Hello everybody. In the first two units, we have seen the brittle and ductile fracture, energy release rate, that is the G1. We have seen the Griffiths experiment. We have seen the R curve. We have seen the plane stress and plane strain condition, that is thick plate versus thin plate, and critical energy release rate. In the second unit, we have seen the stress and displacement fields for various cracks such as edge cracks, embedded cracks. We have seen the relationship between G1, that is the energy release rate, and K1, that is the stress intensity factor. Now we'll start with the third unit. Now this is the syllabus for the third unit, which includes, now this unit is about the plasticity around the crack tip. So we should be able to see the shape and size of the plastic zone which is nearer to the crack. Now the crack length A, we have seen the expressions. The effective crack length is different than this, which we'll see. Now the plate thickness also affects on the plastic zone. We will see for the plane stress and plane strain condition, that is the thick and thin plate. We'll see the J integral and crack tip opening displacement concept. This is CTOD, crack tip opening displacement. Now to start with, in the unit 2 we have seen the stress and displacement fields. Now this we have assumed that the material remains elastic at the crack tip where the stresses are large. But this assumption is difficult to accept because most engineering materials, they do not remain elastic at the high stresses. Now at the crack tip, when the R tends to 0, that is very near to the crack tip, if we see the equations, they give the infinite stresses near the crack tip, which is known as stress singularity. We have seen the concept of linear elastic fracture mechanics. But in real materials, the stresses are not infinite, they are finite, because the crack tip has certain radius, which is a finite number. Thus, real conditions, the material near the crack tip deforms unelastically, that is plastically. We have seen the mechanism of plastic deformation, which is nothing but nucleation and motion of dislocations. Now, there is one advantage of plastic deformation near the crack tip. Now the flow of material near the crack tip makes the crack tip blunt. Hence the stress, it decreases. Thus the catastrophic failures can be avoided if there is a plastic deformation at the crack tip. That means wherever there will be a local plastic deformation at the crack tip, that will help to reduce the catastrophic failures. That is the positive side of a plastic deformation at crack tip. Now the example is given of the diamond. Now diamond is a one material which is not able to release the high stresses. Hence it has the low toughness. In diamond, the interatomic bonds are strong. Hence, the material does not yield near the crack tip. hence the plastic zone is not formed and the material toughness is very low. That means the formation of plastic zone is very necessary for the material to be tough. Now the Chinese proverb says that the trees which bend under the blow of high velocity cyclone survives better. This we can relate to the plasticity and the stresses. That means to survive against the danger of high stresses, the material should be able to deform plastically near the crack tip. Now in this chapter we will discuss the plasticity in case of metals only. We will see the shape of plastic zone and we will also see the factors which control the size of plastic zone. Now in fracture mechanics, the designer tries to avoid the failure. Hence, he prefers a large plastic zone at the crack tip. Now this is contrary to conventional designing, where the designer tries to avoid the yielding. Thus, the size of plastic zone, it is regarded as a parameter representing the toughness of the material. That is, more the plastic zone, more the tougher the material. Now, there are two stress criteria, von Mises and Tresca. We can use this to see the size and shape of the plastic zone. Now, near the crack tip, the material is, the deformation is plastic, whereas away from that it is elastic. So if you want a rigorous analysis, there will be two sets of equations, one for the plastic zone and one for the elastic zone. Now the surface which is common between these two zones, it is not known, and hence it will require the rigorous analysis. This rigorous analysis is complex, hence we will see only the approximate solutions. That means we will only see the approximate solution and we will try to find out the interface between these two zones, that is the plastic zone and elastic zone. We'll see this on the next slide. Now, to know the interface between the plastic zone and elastic zone, we will start away from the crack tip. Now suppose this is the crack tip. We will find the stresses very away, that is the area over here, and then we will move towards the crack tip. And wherever the material will yield, that area we will mark as the point between the plastic zone and elastic zone. We will see the example over here. Now this is the crack tip, this is the direction 1. So in this direction x1 we will calculate the stresses. For example, we calculate the principal stress in direction 2, that is the sigma 2 2. Now away from the crack tip, this principal stress is low, and whenever we are going near the crack tip, it increases like this. Now when we are moving in this direction, here the material yields in this particular case. So this point is a yield stress. Now this is the interface between the elastic zone and plastic zones. That means here in this area there will be a plastic zone, and from this point onwards there will be elastic zone in this direction. Now here we have made one point on this line, horizontal line, that is a 0 degree. Similarly, we can draw n number of radial lines, suppose 10 degree line. Then we can also plot the stresses and we will see that point on that 10-degree line, that is the interface. Similarly, we will see all the points from suppose 10 degree, 20 degree, 30 degree up till 360 degree. We will join those points, and those points we will give, that will give us this size of the plastic zone, and outside that will be elastic zone. Thank you.